Let me say it again. Are there any questions on this?
No.
Okay. All right, cool. Okay, so let's keep going then. All right. Okay, so I just want to do some more stuff with exponents. I'm hoping to start section P3 today. There, I'll go a little bit slower because I will treat that as new. We'll see polynomials. So now let's look at this. Let's now look at this with more exponents. So I just threw in another example here. Suppose a is a real number, and let's say we did a cubed, right? And let's say we're squaring that. So we have a cubed, and then we're squaring this, right? Well, a cubed times a cubed, okay? We're multiplying these things. Well, that's what this is equal to, right? When you square something, you multiply it by itself. That's how we get from here to here. But remember, we're multiplying like bases, so we add the exponents. That's what we're doing here. Okay, and what is this equal to? Well, this is 6, which is the same as 3 times 2. 3 times 2. So altogether, we have a cubed, a to the third, squared, is a to the 3 times 2. And hopefully you can see from here, at least get an idea as to why the next rule is true. Namely, if you have a real number a and 2 integers m and n, a to the m raised to the n, that's a to the m times n, which is a to the n raised to the m. Just another exponent rule that would be good to know. So we have, so this is what we have. And again, up here, this is giving you an idea as to why this is true. Although this is not a proof, because m and n could be any 2 integers. And again, we're still sticking with that convention from earlier. Let me go back to it quickly here. When you have an equation, we're making the assumption that both sides exist. So here, for instance, if m or n were negative, but not both, we also assume a is not 0. So if one of the exponents is negative, we must assume that a is not 0. Again, that's the convention the book is taking. So as an example of this, I'm just playing around with this rule, but 8 to the 4, well, 8 we know is 2 cubed. 2 cubed raised to the 4th, that's equal to 2 to the 12th, right? 2 to the 3 times 4, 2 to the 12th, which is this. 4 to the 10th, right? Well, 10 we know is 2 times 5, which is 4 squared raised to the 5th. And that's, of course, the same thing as 4 to the 5th raised to the 2nd power. I'm using this rule again. And again, if you can write this out using, a calculator, namely here. So I'm just playing around with the exponent rule, so to say. All right. And here are just some others. For any 2 real numbers, a and b, and integers n, okay? For any 2 numbers, a and b, and integers n, a times b to the n is a to the n times b to the n. So you have a product raised to a power. This actually relies on the fact that multiplication is commutative. In other words, you can multiply any 2 numbers you want in any order. You can multiply in any order you want. That's better. That's really that's why this is true. And from here, we also have the, I guess, the analog for division. A divided by b to the n is a to the n over b to the n. And this I threw in here as well. You know, if you have a over b to the -1, you just get b over a. Again, if the exponent's negative, you flip it. You do 1 over, which is the same for a fraction as this. This is actually a good equality to know. It's easy to see algebraically. And just some quick examples. If you do 3 over 2 to the 4, just by here, which is actually based on multiplication of fractions, you get 3 to the 4 over 2 to the 4, which is this. And over here, 3 over 2 to the -1. Again, using these equations, you get 2/3. You just flip it. Inverted, that is. It's also called taking the reciprocal. Yes?
How come for the example 3 over 2 and then -1, you just got 2 over 3, but then for the one where it's like a over b with the -1, you had like the 1 over a and then over b.
This is an extra step here.
Oh, okay.
That's all.
Oh, okay. Thank you.
You're welcome. I mean, I added it in here because this equation alone is a good algebra, I guess, identity to know. It's easy to show algebraically, but really, in the end, when you have a over b to the -1, you get b over a. Awesome question. Any other questions? Okay. So again, these are just some exponent rules that are good. Now, this is another warning. So when you have a plus b raised to a power, so you have a sum raised to a power, a plus b to the n, that's not going to necessarily equal a to the n plus b to the n. I mean, it could equal it, but it doesn't have to. So it's not like in these rules here where multiplication, a times b to the n, is a to the n times b to the n. With addition, you have to be extra careful. And actually, that's what I'm showing you here. If we have 1 plus 3 squared, well, that's equal to 4 squared, which we know is 16. But 1 squared plus 3 squared, that's equal to 1 plus 9, which is 10. So these two are not the same, in other words. In fact, these two are not the same. So you have to be extra careful when you have addition here. I'm just writing this as a warning because I've seen students in the past, maybe I made it when I was younger. In the past, I've seen people would say something like 1 plus 3 squared is 1 squared plus 3 squared, but I'm showing you that that's not the case. So. Okay, good. So we have that example. That so-called, I guess, warning. Okay. All right, well, let me actually now show you, let me go back to it. Let me show you this rule here, illustrate why it's true when n is 2. It's not a proof because n could be any integer. Let's see why it's true when n is 2. Well, if you do a times b, right, and you square it, okay? Okay, so we know that's equal to a times b times a times b. Okay, that's good. Well, by associativity, right, you can group, when you're multiplying, you can group in any order you want, right? That's what associativity tells us. So we get this. So we have a times ba times b. we have A times BA times B. Right? So in other words, I'm grouping B times A. I'm doing this first. By associativity, I can do that. But since multiplication, you can multiply in any order you want. From here, we get A times B. BA and AB are the same. So we have this. Okay, well now, grouping it again, using associativity again, we go from here to here. And this is just A squared, this is B squared. So we get this here. I mean, I hope that made sense. I'm just trying to illustrate why it's true. And I'm also trying to show you why you need the fact that multiplication is commutative. You know, if that wasn't true, then to get from here to here, you know, we'd be in trouble. I don't think it would be true if multiplication was not commutative. Okay. All right, so that's the end of P1 and P2. I want to start section P3, and I'm going to go a little bit slower. I'm going to treat it as new stuff. This I kind of treated as review. Are there any questions about this? All right, so let me get to the new notes. Oh, wrong one. Here we go. All right, so let me close this. Let me just